mechanics, people do a classical kind of theory, but that is parametrized. You understand? So in molecular mechanics, the parameterizing, then it's a completely different thing. Bringing in some parameters, you can do anything. But from the first principle, if you only take Coulomb kind of interaction, you cannot explain in most cases chemical binding, even chemical binding. So bond formations will not be explained. Interaction energies, basically it means will not come correctly. So the exchange effects, even though they are very small, they are extremely important, and that is basically rooted to quantum mechanics. Okay, so classical explanation is very difficult. So I really cannot say that the electron 1 is here, electron 2 is here, and they are interacting. It is not a question of simply electrons are indistinguishable, that 1 can be called 2, 2 can be called 1. That is also not the problem. The exchange has a further problem, that we are not able to identify a density, as you saw. So that is the exactly problem. Anyway, let me share the screen and just quickly say what we did last time. Please let me know if this screen is seen. Are you able to see the screen?
Yes.
Yeah, you're able to see the screen? Okay, fine. So let me quickly say what are the things that we did. Yeah, so that was the discussion. I think it was a 2-hour class. Yeah, that's why there's a lot of material. Yeah, so we talked of this two-particle problem, and we took a single determinant, which we know is not exact because it's an interacting problem. That is something, again, I repeat. However, it's a description, and it has the right antisymmetry. So I said these are spin orbitals, which are made out of special orbitals. So typical 2 electron, how to write the single determinant for an electron? It's an antisymmetric. So any antisymmetric wave function can be written in terms of Slater determinants, and it need not be a single Slater determinant, of course. So I gave some examples of that. Then we started saying that we actually showed this 1 by square root 2, or in particular for 1 by square root n factorial normalization constant, that there are n factorial terms, and any cross term vanishes, only n factorial times it survives. So the norm of that wave function Slater determinant is n factorial. So the constant is 1 by square root n factorial. Okay. And then we looked at the, let's say, helium problem, how to write the helium problem. Then this discussion that you had about the probability. So we calculated the probability of R1 and R2, taking 1 electron in alpha spin, 1 electron in beta spin, and the phi 1 and phi 2 are the spatial orbitals, which in general can be different. We looked at a single determinant, and then we said that the probability of R1 and R2 is not equal to 0. But when you take both parallel spin, we showed that this part is cancels with this part, and the probability is 0 at R1, R1. The fact that the Coulomb term cancels the exchange term for the parallel spins, for the antiparallel spin, that does not happen. And we precisely wrote that the exchange E comes out of quantum effects. So for antiparallel spin, you have only Coulomb term. So there is no cancellation from the exchange term at R1, R1. So whenever R1 is equal to R2, there is a cancellation. So not otherwise. Okay. So I think more or less that is where we ended. That what happens. So I said for a single determinant, probability density of 2 particles at the same R, the 2 particles essentially means electrons, vanishes if the electrons have the same spin. That's a very important point. Okay, so they have the right physical effects. It doesn't mean that it is still exact, even for parallel spins. I can do better than this, but at least this physical aspect is done. For antiparallel spin, even that is not there. Okay. So I repeated that, and I said in practice or in exact case, what should happen is that for any 2 electrons, as R1 goes to R2, the Hamiltonian becomes singular, and the solution of psi should go to 0. Hence, the probability at any R1, R2 for any two electrons, whether they're parallel or anti-parallel spin, clearly that is not happening for a determinate wave function. So I think we had a long discussion on this. As you can see, I have written many times the same thing. So single determinant cannot be an exact solution. I mean, that is of course clear. That is the reason. And so it is not equal to 0 for the anti-parallel spins due to the use of a single determinant approximation for the interacting Hamiltonian. So at this point that was mentioned, I have said in many, many ways. We can also have a multiple combination of determinants which may correct that. That's something we will not discuss right now, but I'm just saying one can go beyond such things. So I said a determinant is antisymmetric. It does not mean the determinant is exact wave function. A determinant, which is a single determinant, is an exact function. If, however, it is exact for a non-interacting Hamiltonian, then we said that R1 is not 0 for antiparallel spin due to exchange terms becoming 0. So there is no cancellation that is happening between the Coulomb and exchange terms. So Coulomb cancellation cannot be realized. All right. So I think we did this. So we can come down to the next slide in today's class. So I would say that maybe I will introduce now the basic variation method which will be required, because now the next thing would be to actually calculate the matrix elements, which Professor Sen will start, because that will take little time. So as we discussed yesterday, on Monday, we will do the variation method, I think. Is that all right, Professor Sangita? Hello, am I audible?
Yeah, that is right.
Yeah. So I said that now we come to the actual case of solution. The problem is that if it is an interacting Hamiltonian, we have come to a conclusion that a single determinant is a valid wave function, but is not an exact wave function. And in fact, for interacting Hamiltonian, exact solution is not possible. You cannot decompose the Hamiltonian into sum of one particular Hamiltonian. So exact solution is not possible. So there are various methods of solution. So one of the methods is called the variation method. So we are leaving this topic of antisymmetry, Coulomb, and exchange. We will come back when you go to the Hartree-Fock, when she will be actually deriving the matrix elements, how to calculate the matrix element. Remember, what we discussed so far was not in terms of energy, but only in terms of probability density. I have not actually said for the energy, but the similar thing will also happen for the energy, as you'll see later. But that we will see when matrix elements are derived. So what we are now telling is a general method which will be used to derive the Hartree-Fock. So that is the reason we are doing it. So the general method is that when we do not know the solution, we may resort to approximate method, and this is basically comes under the class of approximate methods of quantum mechanics. So there are two classes. One is variation, another is perturbation. We defer the perturbation till the Hartree-Fock is over. After the Hartree-Fock is over, we will do the perturbation, because as of now, for Hartree-Fock, perturbation will not be required. Although there are many texts which actually use perturbation theory within the context of Hartree-Fock derivation, but standard derivations variation method knowledge will suffice the standard derivation. So the idea of the variation method is the following. There are two very important theorems. So let me also tell you at this point of time a very famous book by S.T. Epstein. Okay, so this is the variation method, something I don't know exactly the title, but variation method in quantum chemistry or something like that. Yeah, either quantum chemistry or quantum mechanics, something like this. So it's a Saul T. Epstein. So a lot of things. It's a very huge book. Of course, I'm only flipping the first few pages, and that is sufficient for us to start with. So it rests actually on the two very important theorems. So one of them is called the Euler Theorem. I will state the theorem. We can see if we can prove this theorem, but this is actually useless theorem. That is the reason the proof is not important, but it's a very important theorem, because this gives you an exact solution through a variation method. Although you will quickly realize that it is a useless theorem. Okay, but it's important to understand the theorem. It was done by Euler. Of course, many of you know Euler. He is a mathematician, basically. So it said, it is the following, that my impetus is to solve this, and I would say that let me take a trial wave function, psi tilde. I'm calling this tilde as a trial wave function, which means I don't know, but I take a trial function. Now the trial function, how do you take? You take certain forms and then change the parameters within that form. So they become trial function. Any set of parameter will give one trial function. You can keep on vary. And let's assume that I take the trial function within a condition that at least the trial function are normalized to unity. Although for a general purpose, this condition will not be required. Okay, this is not going to be required, but for specific things, this is okay. If it is not required, then I will tell you how to just change it a little bit. So then the Euler theorem says, if I take a trial function and I take a functional, I hope all of you know what is a functional. Functional is a function of functions, a scalar number, which is a function of a function. So here the function is psi tilde, and this integral is a scalar number, which I call it e tilde, is a functional. So this is called a functional of psi. Many of you might have heard this term. In fact, the very fact that the density functional theory actually starts with the same idea of a functional, but there its energy as a functional of density, not psi tilde. So that's a different matter. We will not worry. So I take a functional psi tilde, a psi tilde, and then the theorem simply states that if E tilde is made stationary, with respect to psi tilde, which means I vary psi tilde, and for those psi tildes in which E tilde is stationary, okay, this corresponding psi tilde and E tilde are the solutions of the Schrodinger equation. So it's a very simple. So I hope all of you know in calculus variation what is stationarity. Okay, so what is stationarity? That the first derivative of this with respect to psi tilde should be 0. So normally as I write y equal to f of x, dy dx is 0, it is exactly the same thing. So I will write in a way that the del E tilde, del psi tilde is 0 for all psi tilde, and that is very, very important. All arbitrary psi tilde. That means this stationarity is mapped not in a small subspace, but the entire subspace, entire space of psi tilde. If we can make it stationary, then we actually have the solutions. It is such a beautiful theorem. Provided, of course, psi tilde is normalized. If it is not normalized, for a more general function, all you have to do is to divide by that norm. For a more general function, what you take the functional as psi tilde is psi tilde divided by psi tilde. So it is one and the same thing. So if you want to disregard this, then you can just divide by psi tilde. Subject to normalization, how does it actually work? You first calculate a quantity called the Lagrangian, which is psi tilde h psi tilde minus some condition lambda psi tilde, the condition is this must be equal to 1. So you actually vary this Lagrangian and make this stationary with respect to psi tilde and lambda. You can clearly see that when I make this stationary with respect to lambda, I get this equal to 0, which means my condition is automatically fulfilled. So this kind of way is called constrained or variation, or it is called the Lagrange variation. So this is very important in mathematics. Okay, so Lagrange variation. So it means that if I do a stationarity under condition, then this is my objective function, which I'm trying to make stationary, but this is the condition that this must be equal to 0. Then what I do is that do not make this stationary, but construct another Lagrangian, another new function, which is this minus a multiplier, which I don't know the value, times the condition. For each condition, I'll bring in one multiplier. In this case, there's only one condition, so I have only one multiplier. So, or you make this stationary. So when I said that this has to be stationary, it was subject to the condition that this was equal to 1. So what I'm actually going to vary is this Lagrangian. Is this clear? So for example,
Sir, can you repeat the Lagrangian?
yeah. So I go one step. So let's say that I have to vary, I have to make y stationary with respect to f of x subject to a condition that g of x equal to 0. I hope you understand the problem. It's a mathematical problem. So I have a y equal to f of x. So I want to make y stationary with respect to x subject to g of x equal to 0. I hope it's clear to everybody what I'm writing in shorthand. Y make it stationary with respect to x subject to another function g of x equal to. That's a very standard mathematical problem. That I don't want to make it stationary free. This should always be true, right? In such a case, you construct a Lagrangian, which is f of x minus lambda times g of x. So don't make y stationary. Then write del L del x equal to 0 and del L del lambda equal to 0. Solve, because now you have two parameters, x and lambda, right? If you solve these two equations, then you will get the actual stationary subject to this condition. You can see why, because when I'm solving this quantity, automatically this is coming out. What is del L del lambda? G of x. So g of x equal to 0 is automatically satisfied. And then you vary the entire Lagrangian with respect to x. You will get an equation in which will determine both lambda and x, and that's your stationarity. So this is a very simple way of solving a stationarity problem under constraint. You have not done this. Normally what happens, you are given y equal to x square and you say what is the stationarity. So you find out by dy dx equal to 0, you find at x equal to 0, etc. And then you can say it's a minimum, maximum, etc. But if it is under constraint, all you have to do is that do not vary this with respect to x, but vary this. That's the only difference. Instead of this, vary this quantity. Is it clear? If you do that, you will have the variation. So if I give you a function, let's say some f of x, I ask you to vary 3x squared minus 4x, whatever, some value I give you, make it stationary. But then I say, no, make it stationary subject to another g of x, some function of x equal to 0. Then your strategy will change. What you will do? You will make this function minus some constant into this function and vary that. Remember, whenever the conditions are written, it has to be written that equal to 0. That is important when I'm doing it. So that is the only change that will happen. And this is something that you may not have studied. This is called variation or stationarity under constraint. So you bring in a Lagrangian, and this is going to be a very important point even when you do Hartree-Fock, you will see everywhere. So it's very important to understand the idea of the constraint variation. So for every constraint, I bring in a parameter like this. Now, I can have another problem. So I've given f of x, make it stationary with respect to x, subject to g1 of x equal to 0, g2 of x equal to 0. I expand the problem, two functions. Then what will you do? You will again calculate. Yes.
The two parameter comes first. The two parameter, extra two
Yes.
parameter.
Right. So I will do a Lagrangian x, which is f of x minus lambda 1 g1 of x minus lambda 2 g2 of x. You understand? And then vary, make this stationary. So automatically, now I have x, lambda 1, lambda 2, three parameters. Lambda 1 and lambda 2 variation will automatically ensure g1x and g2x equal to 0. And then when you do with respect to x, I will get all the values. Lambda 1, lambda 2x. So it's a three parameter problem. So this is a very standard way of doing variation under constraint. So all you have to remember, if you do this, what is the advantage? The advantage is that I don't have to play with this quantity in denominator. So for example, this entire problem can be removed. In the entire problem, I can remove this constraint. If I remove this constraint, this functional that I'm varying would actually become this divided by this. Clearly, when you do calculus of variation, del psi tilde, this is going to be more of a problem because of denominator. I hope you can understand. Instead, what I'm doing is I'm only varying this subject to the condition that this is 1. And that I'm bringing in here. So nothing in the denominator. And that is a simplification that we try to achieve. I hope it's clear. So if you keep the denominator, I don't need any constraint because it is not necessary that this psi tilde has to be equal to 1 when I'm varying. But it is a desirable condition. I may impose it without any loss of generality because I know in my Schrodinger equation, I can always multiply psi by any number, right? I mean, the equation will not change, right? So the Euler theorem essentially states that if I do this stationarity subject to this condition of psi tilde minus 1, which means I actually vary this at a constant variation, then at this stationary point, the solutions are the solutions of the Schrodinger equation. So if I write this L tilde as psi tilde is psi tilde, of course psi tilde can have any number of parameters, minus lambda psi tilde minus 1. And if I make this del L tilde del x, all kinds of x is not one x, there are parameters, right? I mean, it's not one variable, but I'm just generally writing, or I can write simply psi tilde. And del L tilde del lambda equal to 0, I would actually solve the stationarity problem. Then the solutions will be the solutions of the Schrodinger equation. And of course, with this solution, psi tilde is psi tilde will be the energy. This will be the exact energy at the stationarity solution. At the stationarity. So essentially, the variation method is a simple calculus of variation problem. I come up with a stationarity and then I say that this is equal to 0 is a solution. So I actually can get all, and not only that, I get all the solutions because there is not one solution. I hope you realize in a multiple variable like this, there will be many stationarities. And each of them will be a solution to the Schrodinger equation, which is beautiful because we know Schrodinger equation also has exact many solutions, right? We normally write H psi I equal to E I psi I. So all the solutions will be obtained by the stationarity because the stationarity condition will not provide only one solution, it will provide many, many solutions. So if you see this theorem this Euler theorem, you will immediately tell me, okay, I don't need anything else in quantum mechanics, right? If I can do this, all my problems are over. Not only ground state, but excited states, all solutions of the Schrodinger equation are available. Except the Euler theorem says something which is something that you should not miss. It says that when you are going to make this variation, you must vary over all psi tilde. Entire space. Okay? And with the multiple variable that you have, this will actually become an infinite dimensional problem. Whatever the way you take the variable, so this will become an infinite dimensional problem. And in practice, the Euler theorem is unusable. Again, for interacting problem, for non-interacting, it's not a problem. You will get a solution. So this theorem would be extremely unusable because it will have an infinite dimensional problem. If you want to convert this into number of parameters, it will be infinite parameters, so it will be infinite by infinite equations. Because this is the catch here. So it's useless. So what we want to do is in a finite space or in a restricted subspace, it is often called a Hilbert space. I will not mention that name, but in a restricted subspace. So what is useful is to have a variation under restricted subspace. But then there is no exactness, unfortunately. But there is something that we can do which is useful, which will come from the next theorem. Now, please remember that this particular theorem, that subject to this being 1, the variation of this functional gives you exact solutions. I have not proved it. I have left it as it is because of the lack of time. Maybe in one class I can come and prove it. Sangita, when we will have a tutorial kind of class, that every week there is a tutorial, so just let me know. Okay. Hello. Hello, Sangita is there?
She's not there, sir.
Okay. So I will tell her that when there will be a tutorial class, so one of the 2 hours, maybe Monday, whatever, so I can come and prove this. Okay. But today I wanted to finish the theorem that she might require for the Hartree fork. And anyway, this is a useless theorem. We really don't use it. So then we have the next theorem, which is called the Rayleigh variation method. It's a Rayleigh theorem, and this is a very, very useful theorem. So I will prove this. It's a Rayleigh theorem. So 2 gentlemen, Rayleigh and Ritz, of course, all of you have heard their names, very famous people. They actually came up with this theorem. The theorem says the following. Again, I can assume without loss of generality, psi tilde. So that's a condition that I can impose. The psi tilde is equal to 1. So subject to this, what the theorem says, that any trial function, psi tilde, h psi tilde, is always greater than or equal to E naught, exact E naught. This is exact. This is a trial function. Subject to this. If you don't want to subject to this, then the theorem can be generalized to say that psi tilde is psi tilde divided by psi tilde is greater than or equal to E naught. I hope this statement is clear. That is, if I take any trial function, any arbitrary function, and then calculate this average value of the Hamiltonian by dividing by the norm. If you have the subject condition, then you don't have to divide by norm. Again, these are identical. This is at least greater than or equal to exact E naught. E naught is the ground state. I have already told you A psi I equal to EI psi I, we are writing normally from I equal to 0, 1, 2, 3, etc. And E0 is the lowest state. So this is often called the upper bound theorem. I hope why it is called upper bound is very easy. If this is E0, this quantity is always above this. It can be anywhere, but always above this. For any function psi tilde. So now I don't care. Even if I take a restricted subspace, all of that functions will be at least above E0 or equal to E0. In which case, if this theorem is true, then for a restricted space, whatever I am able to do for a restricted subspace, the minimum of psi tilde is psi tilde divided by psi tilde is the closest approximation to E0. I hope that is now clear to all of you. Right? Because all of them are above, so the one that is the closest, that is the minimum, is the closest, right? Is the statement clear?
Yes, sir.
Hello? Yeah. So we will not only, so there is no question of stationarity here. Please understand. This is just a quantity which is always greater than or equal to naught. So here we'll have to minimize it. Minimization, of course, is stationarity, but more than that. I have to minimize this quantity, and that will not be exact E0, but that will be the closest approximation to E0. And this theorem will go over to theorem 1. If you leave this space as large as possible, then what will happen? The minimum will actually crash here, which means it will become equal to, which is basically the theorem 1. All solutions are there. I hope, is it clear? The theorem statements are clear? And you can see in a limit when this space is becoming infinity, theorem 2 will actually lead to theorem 1, at least the ground state. Because in theorem 1, it says I have all solutions. So it also has a ground state solution. Here we are saying that the minimum is always greater than or equal to E0. So if I have an exact space, if I continue to vary this onto a full exact space, then it will become exactly equal. But if I do a restricted variation, at least I have this as an approximation that within this subspace, I can say the minimum value is the closest approximation to E0. So that is the operational way that I'll vary, because I can't have an unrestricted subspace. So it will never actually become equal. It will be greater, but the minimum will be the closest to E0. Is the statement clear? That is why variation method is called approximation. And the approximation, of course, gets better provided you take a larger and larger subspace of variation. Hello? Hello?
Yes, sir.
Yeah, is it clear, the statement?
Yeah. Mhm.
Yes, sir. One thing, should it be lower bound or upper bound?
Hello? Yeah?
Yes, sir. Should it be lower bound or upper bound?
No, it is called upper bound, not lower. The values,
Okay, sir.
these values are higher than this. That is how it is called. So E0, it is not lower bound. E0 is bounded from the top. Do you understand? So that is just a question of nomenclature. Okay. It means that the E0 is here. These values bound E0 from the top. That means these values will never go here. You understand?
Okay, sir.
So this is just it's an English word, so don't worry. I mean, if you think lower bound, you are thinking in a converse manner. That's all. So that is not the very important point. It means that the E0 is bounded from the top. From the top, whatever values is there, from the top it is bounded. We know that the E0 has to be lower than these values. So that is what is meant by bounded from the top. Okay. So this is the operational way that the variation method is actually works. That the minimum becomes the closest approximation to E0. All right. So what we are going to prove is just this, that for any psi tilde, it is greater than equal to E naught. All right. So let me now give the proof for this. This I'm going to prove, though I have hardly 15 minutes, not even 12 to 13 minutes, but I think we should be able to prove. So let's take a function psi tilde, and I know that I have eigensolutions of Hamiltonian, which exist in principle, psi 0, psi 1, psi 2, etc. I can always expand in principle from I equal to 0 to whatever infinity by the solutions of the Hamiltonian. This is I don't know the solutions, but I know that this exists. This is an existence, right? My trial function can always be expanded in terms of the exact functions. Is it clear? Because they form a complete orthonormal set, right? Although I don't know this. So if I don't know this, I will not be knowing the Ci tildes. That's also fine. But an expansion exists. If it exists, then let me see what is psi tilde, is psi tilde. First, I'm going to use the condition that this is equal to 1 a little bit later. So what is this? Can you quickly do this? Sum over I expand this with the two different dummy indices, right? So this will become, let's say I. So Ci tilde star. This will become J. So it is Cj. And then psi I will come on the left, H psi j. Can you see this very quickly? So I have expanded the psi tilde as sum over I, Ci star, psi I. Conjugate, right? H, and this psi tilde on the right as sum over J, Cj, psi j. Is it clear? And the integration will be over this, because these are numbers. Hello, all of you can see this? Hello?
Yes, sir.
Yes. Now you know that the psi I and psi j's are eigenfunctions of the Hamiltonian. So this is going to be a diagonal matrix, right? So H psi j is Ej psi j. Psi j's are orthogonal to psi I. So I can write this as sum over Ij, Ci star Cj, Ej, right? And then delta Ij. Note that H psi j is Ej psi j. Psi j psi I will now be integrated. Ej will come out. Integration of psi I psi j will give you delta Ij. I hope now all of you can do this by now. So I can write in this manner, which actually leads to Ci star Ci Ei. Because j must be equal to I. Is it clear to all of you? Sorry,
Yes, sir.
I have to make tilde. Yeah, that's okay. So this is equal to sum over I mod Ci tilde square Ei. So this is exact energy, remember. But this is the trial coefficients for this wave function. I don't know any of these, of course. But this is only existence. Is it clear? Hello?
Yes, sir.
Yes. Now I have another condition. Let's not forget that condition, denominator. I have put this equal to 1. I expand exactly in the same manner. So this on the left, this on the right is I and j. So Ci tilde star, Cj tilde. And here it will be very simple. Instead of psi I, H psi j, the H will go out. It is going to be simply psi I psi j, which is delta Ij. So this is going to be sum over I. I think I can write mod Ci square equal to 1. Is it okay? Because this is a delta Ij, j will be equal to I, so mod Ci square, and this must be equal to 1. This I know. So remember, my psi tilde 1 has actually resulted in the fact that this coefficient, whatever it is, mod square, if I sum over all of them, must be equal to 1. I don't know these coefficients. Please understand. I only know this condition. This is nothing but this condition. So now I am saying, I'm not doing any variation here. I have to only show that this quantity is greater than or equal to exact E naught, subject to this condition. Is it clear? The content of the proof will now be that this quantity, which is psi tilde H psi tilde, must be greater than or equal to exact E naught, subject to this being 1. Right? Hello, is it clear? So that is what I'm going to prove now. That is what I'm going to prove now. So let me start with this condition. So I have to prove, let me write it again. Sum over I mod Ci square Ei is greater than or equal to E naught. This is what I'm going to prove. Subject to sum over I mod Ci tilde square equal to 1. So it's just a mathematics. This is mathematics class, huh? Because variation theorem is nothing to do with just chemistry. It is chemistry, physics, engineering. It's a mathematical tool. You know, some of you might have even learned in mathematics course if you have taken. So I'm sorry that this class is actually a mathematics class, but you cannot help. Variation and perturbation theories are mathematics. Okay, and they will have a bearing in quantum chemistry. So this is all I have to prove now. If I prove this, I have proved my original statement of Rayleigh's variation method. So let me look at this proof. Let me look at the left and the right hand side. So let me write down for this left hand side, which is sum over I mod Ci tilde square Ei. Let me break it up. First write C tilde 0 square E0 plus C tilde 1 square E1 and so on. Is it clear? So I keep on writing infinite space. This plus this plus this, etc. If this is not clear, this is square. Huh? So this is my left hand side. Look at the right hand side. Right hand side is only E naught, which is exact ground state. These are all exact states, remember. Okay. Then I multiply the E naught by sum over mod Ci square without anything, because that is equal to 1, right? Do you agree? So what I am doing is E naught into 1. Well, I know that this condition is equal to 1. Now I expand this. What do I get? I get C0 square E0 plus C1 tilde square E0 plus C2 tilde square E0 and so on. Because these are all expansions, C0 square, C1 square, C2 square. All of them are multiplied by E0. Is it okay? Can you see this and this? So here it is Ci square Ei. Here it is same Ci square sum, but with E0. Hello? So I'm trying to prove that this is greater than E naught, subject to this condition, right? Subject to this condition. So to prove this, I've taken the left hand side, I've taken the right hand side, and I'm going to compare and show that this is greater than equal to E naught. But while doing this, I recognize that there is a condition. So I multiplied the right hand side by that condition, that is equal to 1. The condition is equal to 1. I've used this condition. Is it clear?
Yes, sir.
Now what I'm doing is to compare these two, term by term. The first term is identical, right? But second term onwards, there is a change. This part is always the same, but these parts are different. And remember, the parts which are same are always positive. I'm just making an argument which I'll write because it is mod square. They're always positive. So a positive quantity is multiplied by E1. A positive quantity is multiplied by E naught. So let's look at these two terms only. So mod C1 square E1, mod C1 square E naught. Which is greater? Tell me, which is greater among these two terms?
The left one.
Yes. It can be greater or equal. Because E1 by definition is greater than or equal to E0. However, this is important to realize that this is positive. If it was a negative, then things would have changed, right? A positive quantity multiplied by a larger number remains larger. But if negative quantity by a larger number, then it will be difficult, right? So then it becomes opposite. So the point that I'm trying to say that term by term, if you now compare, every term, this quantity is greater than or equal to corresponding quantity. And I can now say, so this is true for all Ci square. Ei is greater than or equal to all Ci square E0. And this is fairly correct. Even for I equal to 0, I can write this because I have written equal to. So term by term, they're equal, either equal or greater. Hence, I can now argue that the left-hand side is greater than or equal to the right-hand side. Which means the mod Ci square Ei is greater than or equal to E0. Because all of the Ei Ci tilde. I don't require the value of ease, exact ease. See the beauty of the proof. Whatever be the values, this will be true. And this is nothing but psi tilde, psi tilde. And this is, of course, the statement. And this subjective condition comes here. That is used here by multiplying by 1. So we have proved that the psi tilde is psi tilde, which was my left-hand side, which was basically mod Ci square Ei. Sorry. So mod Ci square Ei. That psi tilde is greater than or equal to E0, which is the right-hand side here. Because this is equal to 1. So, of course, subject to the condition that psi tilde is equal to 1. So, don't forget this. Otherwise, you have to divide. And you can still prove it. You can still prove it. The proof becomes somewhat more complex. I don't want the denominator. So, I have proved the Rayleigh-Ritz variation method that any function, any arbitrary function that I take, the average value, provided the function is normalized, and the average value written in terms of denominator is still greater than or equal to 1. In any case, the statement of average value is always right. Because if it is not normalized, you have to divide by psi tilde, psi tilde. So we are saying that the average value of the Hamiltonian. So this is a statement which can be generically made of the Hamiltonian in any arbitrary function is greater than or equal to E0. So that is a fairly correct statement anyway. So you don't have to worry about normalization. And then what will happen that within a restricted subspace, as I told you, the minimum value will be the closest approximation to E0 for any variation. Of course, I will not take only one value, only one arbitrary function. I have to keep on varying so that, because we don't know how much greater. That's the problem. If greater is okay, but if it is greater very large, then it is useless. So I have to take a subspace and minimum. And obviously, the variation method will work best if my subspace is larger and larger. Right? So this theorem too is really an operational theorem. But this is not a stationarity alone. This is a minimization. That is what I'm trying to say, the minimization. That's important. So eventually I have to minimize it. Okay? Yeah, I hope it is clear. So this will be used later for Hartree-Fock. So I thought I will finish it. For the Euler variation, I'll come back and try to prove it. It's also very useful. It's also very, I would say pedagogically very good to know that you can get exact solution. Though we can't actually use it. But that's a different matter. Sometimes in mathematics, such existence is very important. That it exists, that all, and in this case, it is not minimum. All stationarities. Minimum is always one, absolute minimum. But here, lots of stationarities there. All of them are solutions. That's a very beautiful thing to know. And if God would have told me how to make all of them stationary, then my entire quantum chemistry would have been over, right? So that's a beauty of this statement. So I'm going to come back. Right now it's 10 o'clock already. So I'm going to come back in one of those tutorials. I'll just tell and try to prove this. And I think from tomorrow, Professor Sangita Sen will start the class. I was planning to take tomorrow's class, but I have another meeting in the department meeting. So in the afternoon. So I will not take the class. And anyway, next week, she was supposed to start the class. You have 1, 2, 3, 4, 5, 6, 7. So yeah, all 7 of you are there. So please try to be attentive. That is important because, now things will actually get, because now with all these determinant, we will try to calculate the energy, and then we will try to ask this question, what is the best determinant? Single determinant. We know it is not exact, but still, what is the best among all? And that will be Hartree-Fock approximation. And then we will see all features of Hartree-Fock approximation, because single determinant is still chemistry. So Hartree-Fock is something that you can associate with chemistry. Molecular orbital theory that you have learned, MO theory, is all Hartree-Fock. And then we will see what are the problems of Hartree-Fock. And one of the problems you have already known now, that the probability at R1 is not 0 for antiparallel spins, right? We have done that. Because that is true for any single determinant, so it will be true for Hartree-Fock. There are other problems. How do you go around? And that is when the electron correlation will come in, beyond Hartree-Fock, okay? Which you have not defined what is electron correlation. So it will come in, and Hartree-Fock will already use variation method. When you go beyond, it will also use variation method again to go beyond, but it will also apply perturbation theory. So that time perturbation will be done. So I think there's a lot to do. First of all, the Hartree-Fock has to be finished. And remember, when you write single determinant, it is always in terms of spin orbitals. You cannot write a determinant with just spatial orbitals. But you can come from spin to space by some integration. Just like we did the probability of R1. What we did? We integrated the spin, you remember. And that is when I said the certain effects for antiparallel spin cancel. What appears to be an exchange term gets cancelled. And then at the probability at R1 doesn't get cancelled, because that was very important to cancel the Coulomb term. Okay? Whereas parallel spin, that remains, and then special R1 that cancels the Coulomb part. Please go through that part, that antiparallel and parallel, why the results are different. Okay? So you will know also how to do the spin integration and what are the effects. It's not that for antiparallel it was still a determinant. So I took a 2-electron case. So still both the terms were there. But when I tried to integrate, the exchange term vanished because of spin restriction. But that was exact. There is no question about it. But the fact that the exchange term vanished had an impact on the spatial part when R1 became R2, that it was not cancelling the Coulomb term. It's very exciting, actually. Nothing wrong in exchange term vanishing. It had to vanish because of parallel spin. So the problem was not that the exchange term vanished. The problem was in the origin that I took a single determinant. I hope it's clear. So that discussion which we did in the last class was extremely important. So please go through this. The origin was actually a single determinant. The spin integration when we did, it was exact. There is no problem. Because when I do an antisymmetry, something with alpha, something with beta will actually vanish naturally. We did that for spin orthonormality. But that had a serious impact on the probability for the radial space, for the R space, that there is no scope of the Coulomb and exchange term cancelling for R1 equal to R2. All right, Sangita, I just wanted to tell, since you have come back, that I have finished the Euler theorem, and I finished the statement of the Euler theorem that all stationary solutions are exact solution, and I have actually done the proof for the Rayleigh-Ritz upper bound, which is the operationally what is going to be used. And I have also said that in a restricted subspace, the minimum value thus is the closest approximation to E naught. Exactly, ground state. And remember, this variation theorem is only for the ground state E naught. So far that we have stated. So this is what I have done. I have proved the Rayleigh-Ritz. I have not proved the Euler theorem. In one of the tutorials, you let me know. I will come back and prove the Euler theorem. Okay. All right, Sangita.
Yes, yes.
Yeah. So one of the tutorial session, I'm going to prove the Euler theorem. So maybe half an hour or 15-20 minutes I'll require. Then you can continue. Okay. All right.
Okay.
So all right. Okay. So we'll see you, and you will take the class tomorrow. Yeah, Sangita. Okay, I will come back later. Yeah. In any case, for formally. Okay. Thank you. Bye.